Okay, in this video we're going to look at another type of substitution reaction called the SN1 reaction. Although the SN2 is the most commonly used substitution reaction, in some isolated cases the substitution is going to obey first-order kinetics. And this process is most commonly observed when the substrate is a tertiary, often a secondary halide, and the nucleophile is a relatively poor nucleophile. This requirement for the poor nucleophile is because the SN2 reaction can sometimes take over, or another process called elimination, which we'll look at later, can occur. This requirement is kind of stringent, and often to get a poor nucleophile you just have to use the solvent as a nucleophile. And this type of reaction where the solvent is also the nucleophile is known as a solvolysis reaction. So down below we have a good example of a classic SN1 reaction. Here notice our halide is tertiary. Okay, our nucleophile, sodium acetate, is kind of low on the nucleophilicity scale, right? And we get the substitution product at the tertiary position. Okay, in this other reaction here we're using methanol as the nucleophile, and we're also using it as a solvolysis. So this is a solvolysis reaction. A very common abbreviation we have here is this abbreviation for the acetate anion. So this is an abbreviation you'll see frequently. All of these reactions obey first order kinetics. The rate is just a function of the concentration of only the alkyl halide, and the nucleophile does not enter into the rate equation at all. Okay, what's the mechanism for the SN1 reaction? We've seen this business where tertiary is better than secondary, etc., many times in the past, and it's always been indicative of carbocation intermediates. And that is exactly the case here. This is a carbocation reaction. In the mechanism, we have as our first step, which is also the slow step, and is the formation of a carbocation, or basically a heterolytic bond dissociation into a carbocation and a halide anion. Okay, this is understandably going to be a slow step because we take a situation where everything is bonded and has octets and produce intermediates that don't have enough electrons. So this is kind of a relatively hard thing to do. The second step of the reaction occurs at a relatively fast rate, and it involves simply the coupling of whatever the nucleophile is with the carbocation. Okay? And this reaction, of course, is going to be restricted to halides that form relatively stable carbocations. Okay? If our nucleophile has any degree of basicity, it's going to engage in other processes, like with SN2 substrates it could engage, with secondary substrates it could engage in the SN2 reaction, or it could do the E2 reaction, which is going to be the last subject of this chapter. And this is why we have this restriction to relatively poor nucleophiles basis for the nucleophile in an SN1 reaction. Okay, here is a potential energy diagram for the SN1 reaction. We see that it's two steps. Our first step, the one that's occurring with a high activation energy, is in fact the carbocation formation, and the next step occurs at a much lower energy of activation, and this is a relatively fast step and doesn't enter into the rate equation. This is where we would see the nucleophile, and so since the nucleophile is adding in the fast step, it doesn't occur in the rate equation. Okay, let's look at stereochemistry in the SN1 reaction. You may think at first glance that if we form a carbocation, we're going to see complete loss of all stereochemical information, and that can be true, but this situation here is really kind of complicated. And in the result that you see here at the top, the R2-bromo octane is reacting with water and ethanol and heat, basically solvolysis conditions, to produce the alcohol. And what we find here is that we get a mixture of S and R, but it's not 1-to-1. It's something like 2-to-1. Okay, it's not going within. It's going with mostly inversion, mostly racemization, but not. But there's inversion occurring to some extent as well, and this occurs due to the degree of ionicity of the carbocation. Okay, and this is kind of a hard thing to predict. There are more than these 3 degrees of ionicity that I show here, but these are probably the 3 major ones. Okay, so we can have a contact ion pair, and in the contact ion pair, we're basically we still have a ionic attraction between bromide and the carbocation. So therefore, there's still a backside. Okay, if we attack the contact ion pair, we're expecting our nucleophile to attack the backside like before. Okay, we can also insert a solvent molecule between our halide and our carbocation, but we still have a backside, or we still have the one face more accessible than the other in this case, and we'd also in this case probably predict a backside attack. Okay, and the third degree of ionicity we'll talk about is a free ion. This is where all association between the halide and the carbocation is now removed, and we have a free ion. There's no preference for attack at either face in the free ion. So it's kind of hard to predict the degree of ionicity. So when we are asking, like, what's the stereochemistry in an SN1, you could say, I don't know. And that's actually not such a bad answer. The net result is that the SN1 could result in complete inversion like an SN2, or a complete racemization. Somewhere between 100% inversion and 100% racemization is what you're going to get. Stereochemistry alone cannot be used to diagnose SN1 versus SN2. I guess if you got 100% racemization, you could say it was an SN1. Okay, but if you got 100% inversion, that would not rule out the possibility that it's also an SN1. Okay, so here's a problem. Classify each substitution reaction as SN1 or SN2, and again, pause the video, do it, and then restart it and look at the answers. Okay, so in the first one, we have a relatively strong nucleophile, a primary halide. We're going to see an SN2 kinetics in this reaction. In the next one, we also have a really good nucleophile, a secondary substrate, and this is going to also proceed through SN2 kinetics. Okay, or second order kinetics. This is an SN2 reaction. In the third one, we have a tertiary halide, a relatively poor nucleophile. It looks actually very similar to the example that we showed previously. And this is a good example of an SN1 reaction. It has these characteristics, a tertiary substrate and a relatively poor nucleophile. In the last one, it's also an SN1 reaction. It's secondary. It's neopentyl, so it's not likely to do an SN2. But what we're seeing here is that it's also accompanied by rearrangements. And rearrangements are symptoms that you have carbocation intermediates. So let's look at the total mechanism for this last reaction and see how we can if we can rationalize the formation of all these compounds. Okay. So this compound at the bottom here, of course, is the one that you would expect if there aren't any rearrangements at all. Okay, so here's our mechanism. We dissociate chloride to make a carbocation. Okay, if it's universally an SN1 reaction, we're forming standard product just by taking the acetate anion and reacting it with a carbocation. Okay? Since it's a carbocation adjacent to a tertiary center, we can also migrate the methyl group here. Okay? And if we migrate the methyl group, that's now our carbocation. Our carbocation goes from secondary to tertiary, and we know that's a good process. And the acetate anion then reacts in the last step. Sorry, there's a mistake there. That should be an acetate, sorry, to produce that compound right there. Okay, all of the alkyl groups adjacent to the carbocation have the potential to migrate. So the CH2 group could also migrate as well. So here in the blue pathway, we're looking at the migration of the CH2 group down to where the carbocation carbon is. This produces now a tertiary carbocation, but the carbocation is outside the ring, and the acetate comes in the last step to produce our product. Okay, let's look at a common transformation people need to do in organic chemistry, and that's do the substitution to reaction at an alcohol. We can't really do this directly usually because OH minus is not a good leaving group. Okay? Alright, so how do we do this? One way to do it is to turn it into a halide. Here we'll use either SOCl2 for a chloride, PBr3 for a bromide, or HI for an iodide. This will give us the halide, which we now know can do an SN2 reaction. This is a perfectly acceptable method to do this reaction. However, a much milder method involves turning the alcohol into what we call a paratoluene sulfonate ester, or a tosylate. Okay? So, in this reaction, we're treating the alcohol with this compound, paratoluene sulfonyl chloride, and this compound, pyridine, which is there technically just to take the HCl byproduct and produce a less acidic byproduct, pyridinium hydrochloride, which is the compound shown there. Okay, there's kind of a lot to draw here. So this paratoluene sulfonate group has an abbreviation. Okay, so right here in the box you see what's signified by the letters TS. Okay, so this whole compound here, paratoluene sulfonyl chloride, is now just going to be shown as TSCl, a TS group bound to chlorine. Okay, this is producing a paratoluene sulfonate ester, which again is going to have an abbreviation. Okay, in this case it's butyl OTS, but here we have the tosylate group bound to oxygen. Okay, all right. So it turns out that a tosylate group reacts very much like a halide. In fact, they're interchangeable. We won't get to a reaction where halides and tosylates are not interchangeable until we get to chapter 14 of the textbook. All right. Okay, I went back. Sorry, I meant to go forward. All right, so once you have the tosylate, you could treat it with sodium cyanide, and that would produce the product. Okay. If you look for the relative leaving group ability of a tosylate, it's a slightly more reactive than an iodide, which we know is more reactive than any of the other halogens. Okay, I'm not going to go through the mechanism in detail for this reaction, but I will provide a important detail for some of the problems that we're going to do at the end of this chapter. The bond that you form there is the bond between oxygen and sulfur, not the bond between carbon and oxygen. So just remember that as a guideline for some of the stereochemistry problems that we're going to do at the end of this chapter. Okay. All right, and a final issue that we're going to look at before doing mostly problems is substitution versus elimination. Okay, so Chapter 8 suggests that the product of this reaction of cyclohexylbromide with sodium ethoxide ethanol is this first product on the left here, ethyl cyclohexyl ether. Okay, but you may recall that you saw an almost identical reaction in Chapter 5. And in Chapter 5, we produced the cyclohexene, shown here as our product. Okay, so I guess if I were on the witness stand and a lawyer was grilling me, they could say, were you lying in Chapter 5 or are you lying now in Chapter 8? Well, I guess you could say I'm lying in Chapter 8 because the result of this reaction is that you produce that product in only 5% yield and the other product in 95% yield. We're never really lying. We just, I guess, didn't tell you the full story. And now we're going to tell the whole story. Okay? The E2 and the SN2 reactions are competing processes. Prediction of the observed pathway requires weighing three factors. Most importantly, what type of substrate is it? Is it methyl, primary, secondary, or tertiary? And looking at the nucleophile, is the nucleophile basic or is it, and does it have a high degree of nucleophilicity, i.e. is it far down in the periodic table? Okay. So we're going to look at these substrates one at a time. First we'll look at methyl halides. When we're talking about SN2 versus E2, the E2 is always going, the SN2 is always going to win. It takes 2 carbons to make an alkene. We don't have 2 carbons in a methyl halide. Therefore, you can never do anything but an SN2 reaction. Primary halides. The SN2 is almost always going to win out over the E2. The best we can do for E2 is to use a very hindered strong base, but even then it's actually very hard to selectively form a alkene from a primary halide. Okay, so here are a couple of examples. This iodide here would react with sodium ethoxide. We'll use DMSO since it's a good SN2 solvent. And we find that we get almost exclusively the ether and very little of the alkene. Okay, so our product is this. SN2 wins. With a more hindered alkoxide, these two reactions become very competitive, and you get about an equal mixture of E2 and SN2 products. So we'll say that with primary halides, you should just go for the substitution product, the SN2 product. Okay, for tertiary halides and tosylates, we're going to provide mostly the elimination products. The only hope you have for getting a substitution product is to use SN1 conditions, i.e. use a really poor nucleophile. A nucleophile that has any degree of basicity is going to give us an E2 product. So in this equation, we see that almost all of the nucleophiles that we look at are going to give the elimination product. The only hope of getting substitution products is to conduct an SN1 reaction. Okay, are we done here? Well, if you notice, we did skip something. That's secondary. And secondary is the one that requires that you think about it more than any other type of halide. Secondary halides and tosylates, we have to give a detailed analysis of the basicity and nucleophilicity issues. Basically, high basicity is going to favor E2 products. The more basic it is, the more likely it is to give an E2 product. And the more nucleophilic it is, the more likely it is to give an SN2 product. Okay, so let's take 3-bromoheptane, shown here, a nice symmetrical molecule. If we treat this with sodium ethoxide, we're going to get only the E2 product. Okay. However, the sulfur analog of sodium ethoxide gives almost exclusively the SN2 product, and the cyanide nucleophile also gives predominantly the SN2 product. All right, so how do we explain this? Well, sodium ethoxide is a stronger base and a poorer nucleophile relative to sodium thioethoxide, or NaSET. Thus, the SN2 is more likely with NaSET. Sodium cyanide has a very low basicity and is going to give us exclusively the SN2 product. Okay, so we have to analyze all the factors carefully when we have a secondary halide. Okay, now for each process, we need to estimate whether the SN2 or E2 is going to result. So this is a problem for you to do on your own. And then pause it, then restart it, and let's look at the answers. Okay, the first one, or let's look at what type of halide we have. We have tertiary, 3 secondaries, and a primary. Our fate here is that tertiary, we should, any halide or any nucleophile with any degree of basicity is going to give elimination. With a secondary, we're going to see substitution, primarily with the more nucleophilic, less basic species. The more basic species, shown here with sodium ethoxide, is going to give predominantly the elimination product. And finally, the primary halide with the same nucleophile is going to lead to the substitution product over here. Okay, so these are the predicted products of these reactions. Okay? All right, so I'm going to stop this video right here, and the rest of this is not really going to be new information. It's just going to be additional problems. Okay?